So good morning, everyone. Greetings to all your fellow witches and wizards, and welcome to my talk where we delve into the enchanting matters of SwiftUI animations. You probably know there is a Walpurgis night coming next week, so now it's the time where air is full of magic, and it's time to initiate new apprentices into the sacred knowledges. So allow me to pass some knowledge about the animatables in SwiftUI for the new generation of young witches and wizards that we regularly do at these times, at least for the last 5 years, right? And let's start with a little bit of motivation. I've put together a demo reel, let's say, of the various animations I've done in SwiftUI to kickstart this event. So this was a really tiny sample of what you can actually achieve. In this talk, I will go through what I've gathered in the past years regarding the SwiftUI animations. It will be basically some composition of examples, use cases, and various useful utilities or interesting APIs that SwiftUI provide us with, so we can create either nice animations on better transitions and fine-tune our apps to be even better. But sadly, we need to start with the boring stuff because we need to understand some fundamentals, how SwiftUI actually animates things. SwiftUI, in its core, basically is animate any state change that you are doing in your app. And the state change can be driven from your business logic, it can be driven from your views. It doesn't really matter. You typically have some starting state, then you have the ending state, and then you want the magic to happen. You want SwiftUI to animate this circle from the starting point to the ending point. And for that, you can trigger the animation. You have various approaches how to trigger the animation. First one is using the with animation block, where you define what animation you are using. Here we are using ease in, ease out function with some duration. And then in the block itself, you do the actual state change. So for this case, the move ball, we can say that it's just changing the coordinates of some view or coordinates of some entity to the new coordinates. Another option is that you assign animation to the view itself with the .animation view modifier like this. Again, you can specify animation with other parameters. And then you define what value will actually trigger the animation, which is great because you only want this animation to happen only in some cases, not every cases. And then you don't need to change or call it explicitly in with animation block. So anytime the ball.x value changes, then the animation will happen. Let's go through a couple of examples. you can see that with this animation modifier, you can change those and apply different animations for different state changes. So here we are doing spring animation when the rectangle height is changing, and ease in out animation when the width is changing. This works great. In various scenarios, but there is one important thing to note, that there shouldn't be a big relationship between what these animations are affecting. So for example, here we assign one animation, then we do rotation effect and do another animation, define it, and you can see that it's actually using two various animations for these changes. If these animations would be depending on the same values or affecting the layout in the same manners, then only first animation would be used and the second one would be omitted. And as I said, the magic actually lies in this protocol called Animatable. This protocol actually features the main animatable data, and this is the property that SwiftUI looks for, because it then uses this value to actually do the interpolation during the animation. You can see that the animatable data is type of vector arithmetics. I will explain just in a minute why this vector arithmetics is critical. But for our current knowledge, it's important that basically what SwiftUI provides us with, CG floats, CG points, they are all implementing these protocols. And if you need to animate more values, then you can use an animatable pair, which basically combines two animatables together. And if you need more, then you can nest those animatables pairs together. So if we have like 4 properties in our view and we want to animate all them together, then we can create animatable pair, which is pair of 2 animatables pair. It's a little bit clunky to use it, but it's completely fine to have it like those. But obviously, you might say, OK, but what if I have 10 or 1,000 parameters and I want to animate all of those? For example, I have a chart and I want to change the values in the chart. How can I do that? Well, the best way is to actually implement your own animatable vector that will implement these vector arithmetics. For the vector arithmetics, what you need to provide is computation of size of the vector, be able to scale it, and be able to do some basic additive arithmetics, which is summing, dividing, and providing the 0 vector. So if we have our own animatable vector, it has its value stored in just plain array, then we to implement these values. And for us, it's basically high school math. So it's summing and dividing and scaling of the vectors. Now, let me explain why this is crucial for the SwiftUI to be able to do the animation. Let's go through some vector arithmetics. So this vector 0, this is our initial state of our properties. It can be just position, xy position, but you can extrapolate to n dimensions. So it can be n-dimensional array. It's the starting state of our entity. And we want to animate to v1, which is the ending state. So SwiftUI does these operations. First, it computes the distance from the starting point to the ending point, just simply by subtracting the values. And then when it's doing the interpolation, which is computing this VA for every time during the animation from the start to the beginning, this vector is actually computed as starting vector plus sized value of the difference vector. So you can see that we have used all these operations that are required by the vector arithmetics. The interpolation goes from the starting point to the ending point according to the animation curve. As we've seen before, we've been using ease-in, ease-out function. You can also use a linear function, which is basically true linear interpolation from the start to the beginning alongside the line, or you can use the spring functions and many others. Now the question is, what if in my case I want to animate once again from the starting point to the ending point, but during the animation I want to go through some intermediate state. So like here, I want the ball to move, but during the movement, I want it to scale to be smaller and then again scale up to be bigger. Like this. For that, we can say, okay, the scale during our time will follow this path. Let's say it's some cosinus path or something like that. How can I do that? We will utilize, once again, Animatable protocol. And for our view, which is this ball, we will provide the animatable data. And the animatable data will be basically the leading information that will control the scaling during the animation. So you can see that this offset factor is basically going from the 0 to 1, from the starting point to the ending point, but we are computing the scale factor that will do this cosinus transformation of the scale during the movement. So to sum it up, SwiftUI looks into your view. It knows it's animatable. It looks into the animatable data, and it will use these getters and setters. And it will interpolate this offset factor. And the interpolation goes from 0 to 1 in our case. But the drawing function itself uses the scaling factor, which is nonlinear and goes along that path. This is, I would say, the most critical understanding that you should get from this boring theory, because it will affect everything that follows. If you have any questions, feel free to ask now. Yes?
How the offset factor changes?
The offset factor is changed from your view or from your business logic, and basically it can be either with the animation block and you set it to a different value. Yeah? So this is just the view, and we will use this. This is our value that we are changing. This is what holds the state. So the initial state offset factor is 0, and then we do, for example, with animation, is in, is out, set offset factor 1. And SwiftUI will interpolate it from 0 to 1 along the animation curve. But during that, we do yet another transformation, and the transformation is this cosine transformation. Yeah? So this is very critical, because if you understand this, basically you can also implement phased animation and the chaining of the animation, because you are now able to fully control what's going on based on your, let's say, timing or offset factor, and you can non-linearly map it to whatever happens with the view itself. I would like to mention also one good practice that works well for me, and I'm usually normalizing all the values from the 0 to 1. Regardless if it's drawing functions, regardless if it's timing functions, it's easier for me to represent it visually without actually seeing it. and it helps me to understand what's going on. I know that 0 is starting point, 1 is ending point. So obviously, if you have like 0.2, you can sort of imagine where it should be, where it will be. It's easier to debug. And the same is for resolutions. I usually normalize everything when I'm working with images to 0 to 1. Because again, if you have point that is 0.5, 0.5, you can easily set that it's in the middle. Whilst if you are working with the true pixels and you have a resolution 4030, 100, 322 to 3800, it's very hard to, or at least I suck at mathematics, so it's hard for me to realize what these absolute pixels are about. So this is a small recommendation from me. Now let's talk about the blending of the animations and timing. Let's consider this example. We have a moving ball once again, and these 4 dots are the state changes. So we are changing states from one dot to another dot, and SwiftUI is animating it like so. And we have set animation duration to 2 seconds and state update, which triggers the animation, once again, happens every second. And you can see that the ball nicely moves along straight line. But now see what happens if we are doing the state updates more frequently. And suddenly the ball doesn't move along straight lines. It starts to follow some curve. And we can even speed it up. And now the ball is moving in circles. It's due to the fact that SwiftUI animations are fully interruptible and they are blendable. So SwiftUI always is trying to satisfy your request, which is animate to your final state. Whilst if there is some animation going on, then it will blend the old animation with the new one. So suddenly, this blend of linear interpolations it will create a nice circle. In iOS 17, there has been a new, I would say, goodies introduced. One of those is Face Animator. This Face Animator allows us to go through some predefined states, phases, during the animation. So here, we are defining that our ball view, we have 3 phases, and the phase affects scale, and it affects the opacity based on what the phase actually is. And the SwiftUI will go through these values provided in the array, 0, 1, and 3, and then it's mapped on the animation, and you can create these let's say, animations that depend on multiple states, multiple phases. But as I said before, this is very, I would say, like a goodie. It's nice to have, but you can implement it also with these animatables, and you can map the animatable data to different outputs by yourself. If you want to have more visibility of actually what's going on, these animation phases APIs allows you to use it like this. So you can actually define animation phases like some enum. You can define what is the state, what is the offset of the view, what is the scale of the view, color rotation, or whatever other entity that you are animating. And then you can provide these phases in the face animator like this. So again, we have the view. We assign the face animator with all the cases of the phases, and just use the phases, the scale effect, offsets, and what we've defined in the enum, like so. It's even possible that for each phase, we can switch between different animation types, between animation, how the animation is being timed. So I would say that this is very readable way how to define this phase and implement phased animations. So especially if you are working in the team, it's very obvious what is going on and what you want to achieve with the animation, even that it takes a slightly bigger chunk of your code. Another goodie that the Swift iOS 17 is providing us is possibility to animate using the keyframes. I don't know if you are familiar with the term, the key phrases or key points or keyframes. Basically, it's something that's being used in, for example, video editing softwares, where you can define the entire curve or chart how some property changes. So, like plot it in the chart in the time, you can say, okay, I want to animation, and my scale should follow this path, my offset should follow this path, and it's being defined during the movement for every single timepiece using these so-called keyframes. So it's not like that you need to provide every value, but I, for example, can provide starting value, then some keyframe in the middle and the ending value. And in the keyframe, I define that the offset should be something and the scale should be something else. And then the SwiftUI and these animation tools that are using keyframes, they will go from phase to phase and animate according to the provided values. The SwiftUI API for this part looks like that. First, we define our structure that will hold all the animation values. At this example, we are changing scale, stretch of the view, and the rotation. On the right, you can see the actual animation that we are trying to implement here. And we are using the new API keyframe animator that takes the initial value, which is this structure first initialized, then the trigger that will trigger the actual animation. It can be changing of some Boolean property or changing of some integer or whatever. Then we define, in this callback, we define how the content of this animation is actually affected. So we take the content and we apply some rotation effect, scale effect. And for each phase, you can see that we are actually reading the value from these structures. And then in another callback, in another block, we define the keyframes, which is the most critical part. We basically define the chart for the animation itself. And this is ugly to be seen at the first time, but very obvious. So for each property that we are changing on our view, we define a keyframe track. We say this keyframe track belongs to the scale property. And there are 3 keyframes at the time, at some times, with some durations. And we say, OK, the first keyframe is linear, so I want to do linear interpolation for that keyframe. Then I want some spring, let's say stops, or again, keyframes. And with this approach, you can define different, for example, here, cubic keyframes, so it follows the cubic spline, etc., etc. Again, it's a slightly more talkative, but very powerful, because these tracks are completely independent one on each other. So what happens in one track doesn't affect, for the scale, for example, doesn't affect what happens for the keyframe track for the vertical stretch. So this is powerful because this is very hard to do with other tools and what other means to be able such nicely control what's going on with your view. So this was the basics. Now let's finally move to something that is more fun. And let's talk about some real usage of animation. So let's say that we want to implement the slider, but we don't want a boring slider. We want a slider that animates nicely, that behaves under your finger in a slightly better way, an organic way. So I have implemented here this slider. I call it a gummy slider that can stretch as you are moving it towards the end of this path. And for that purpose, we need to be able to draw the shape of the slider. And shapes and animations in SwiftUI go well hand in hand together. So let's see how easily it can be implemented. So we have our view that is nice square. You can see it in this dotted diagram. And we are drawing the shape of this slider. And the more we are trying to push the slider out of the bounds of the main slider rectangle, the narrower we draw it, and the biggest extent on top and down we are providing it with. So in the code, it looks like that. We are defining a slider shape, which is of type shape. And you can see again, it's implementing animatable. So we are providing here the animatable data. And in the path, we are actually drawing this rectangle, as I said. So the narrower it is, the bigger it is. It's basically a rounded rectangle from that point. The similar use case here is if you want, for example, implement the app that tracks the amount of the liquids you have consumed during the hour or during the day. So we want the custom shape that draws these nice lines and waves. So again, you can see the cookbook is the same. We are defining the shape. We are providing the animatable data. For us now, it's the height of the water. It's the water level. And then we are creating custom path that along the water level actually creates nice sinusoidal shape using just very simple linear interpolation. So using a lot of points, we are drawing nice wave like this. And sorry, I don't know what happened. And in your app, you can basically then just do the fine-tuning, use it, for example, multiple times in the Z stack, so it's still the same shape, just the water level is slightly offset. And then if I just change the water level, then SwiftUI is able to animate it because we are providing the animatable data that is controlling the water level itself. There are situations when you want to have some animation that is going forever and ever. Of course, you can set the animation and pass it and set it, OK, just repeat it. But there is a great view called timeline view that can be used for these purposes, because timeline view, basically, you repeat any view in it. And then timeline view is regularly updating the view and providing you with some ticks that you can use for animations. So here we have timeline view, and on the canvas we are drawing again this shape we have implemented before, this water level shape. But we are constantly iterating it, and we are using the time as a control factor of the wave offset. So basically, as the time will be ticking, the waves will be waving because we're altering it with this parameter. So here is the example. You can see that the view is now constantly being redrawn. The waves are constantly flowing, but it animates with the changes the same way as before. So if we change the water level, it animates up and down, but the timeline view takes care of this now endless movement and waving of those. Another great example here is that you can define custom shape that is able to morph into another shape. Something like that. So we can say, I want to change the square to circle. So I define a custom shape from multiple points and then change it. And for that purpose, our animatable vector that we've seen in the beginning is a great way to be used. And there are numerous usages in the real-life applications to be used for such morphing of the vector shapes. For example, you can have such Tinder-like app that morphs the clip shape of the images based on the user actions. Or you can create completely new HUDs or UI widgets just by creating custom shapes and changing them parameters. And SwiftUI provides you with nice interpolations between the states. Another example might be if you want to create something really magical or to have some let's say, visual effects in your app, you can create fire effect again using the shape layers. And the shape layer here for this fire is being defined like this, that you take the starting shape of the view. Here it can be the heart shape or whatever path you are providing it as a starting path. Then I'm computing completely random offsets along that path and filling it with the contour, creating a new shape, and it is actually the shape of our fire. So there are, in this example, there are 3 layers created with the same algorithm, just one is smaller yellow, another is bigger with orange, and another is the biggest with the red. And it's faking nicely the feel of the view on the fire. Another way of SwiftUI animations is utilizing the view modifiers. The view modifiers itself are the big power that you have in your hands when you are creating the apps. And it can be used, for example, for particle effects. How to build those in 6 little steps? Well, first, you define your motion. Here I'm using on this example, I'm using geometry effect that alters the view in the projection space, but you can completely fine use what we've seen in the first part, or we can use phased animation, whatever. We just define some movement, and we wrap it into view modifier. The second step is multiplying those views. So here we are just taking we are creating a Z-stack of a number of clones of the view with this view modifier. So it creates a swarm of views that are moving alongside this path. And the last thing is that we just want to fine-tune it so it looks nicer. So the animation is still flowing. It's repeating forever, as you can see here. And we only add some scale effect that, again, takes some time controlling parameter. And we also can change the opacity that, once again, takes the source time and changes the opacity of the moving view. the creativity here is not limited, so whatever you wish, changing the hues, changing the views, it can be up to you. So the final animation can look like that if you are trying more. But you might ask, okay, but how many views are there? I would say a lot, let's say 100, 200. Is it really the best way to create particle effects in SwiftUI this way? Well, not, even though it's the best to actually experiment. And also, it's the best that you can reuse it, that everything is wrapped as the view modifier, so you can reuse it across your app. So another way is that you will create everything as a single shape. So I have now multi-particle shape, and in the path itself, I'm drawing a lot of instantiations of the particle itself. This is much better, much more performant, but then we are losing ability to actually blend between the various layers and blend effects of each particle. Here is an example of this multi-layer shape that is basically trying to simulate the Chladni patterns. I don't know if you saw it somewhere, but it's like that you have a plane with sand and you are playing the music, and the sand is forming this diagram based on the frequencies. But actually the best way how to implement it is using Canvas, because Canvas is very performant in terms of rendering operations. So we, again, are using what we've seen before. We have a timeline view that is providing the time for this endless animation. Then we have a canvas where we are doing the drawing itself, and the drawing is just in the for loop of number of particles. We are drawing these particles based on some computation of position and alpha that happens here. So you need to simulate it, everything together, but it's the best way in terms of performance to do it like so. So I'm very behind the schedule. So I will skip this part. Basically, what I wanted to showcase here is that the view modifiers itself are very handy in terms of messing with your view and using the content in the view modifier multiple times can lead to nice either effects or transitions. So let me at least finish with this one. So we have a view, and we want to create a transition that the view splits and move away from our view and then can be replaced, for example, with another view. So what we will do, we will divide the view into quarters and move each quarter to a new place. And everything is wrapped in the view modifier. So this slide part modifier, it takes a source view, and you can see that we are creating a Z-stack, and in the Z-stack we are creating 4 copies of the same view and masking each part with mask shape, only taking, let's say, half, top right half, top left half, and so on. And we are moving the content, these halves, with the offset modifier, again, with some offset factor that goes from 0 to 1. And this view modifier can be then used to create the transition, such as this, any transition.modifier, and then we define that we have active state and identity state, and we only say that for the active state, it's this modifier with offset factor 1, and for the identity, it's slide modifier with offset factor 0. And that's all, and we have a new transition, and we can use it when we are changing the views in our app. So that's all. If you want to know more about shaders and other things, we can continue in the speaker's corner. I'm sorry that I was too slow today. but hopefully I've managed to motivate you to look into the SwiftUI animations and actually joining this cult of magicians in SwiftUI. Thank you.
We have 5 minutes for the questions, so let's see Slido, and I can read it. Okay, so the first question is, did you ever have a good use case for transaction keys in your animation?
I don't.
That was fast. Another question is, will you share this great presentation deck after mDevCamp?
Yeah, and I believe you will be sharing it, right?
Yeah.
So
will you
it should
post
be
it
there
on your
and
social
you can,
media?
Sorry?
Will you post it on your social media?
I can post it
Yeah,
as well.
okay.
Yeah, sure.
Maybe faster.
Yeah.
Great. What is the performance impact of SwiftUI animations compared to Metal?
This is a different thing. Well, the animation itself are very performant. It only depends on actually the drawing functions. And the drawing functions can be metal-based or non-metal-based. What I missed is I have a couple of slides related to this performance. So just briefly, when you are doing crazy animation like this, you always need to check number of views that you are using. The less, the better. Then, if something is really consuming a lot of views, try using the canvas that I've shown you before, or direct drawing using the shaders. But this is usually like the last resort that you are going with. Sometimes it's completely fine when you call the drawing group view modifier on the view itself, because it will enable metal acceleration for the drawing of the view itself. And that's basically the main rules that you need to observe. So the less, and of course the cost of the drawing functions. So the more blending, the more blurring you are doing, the more you are affecting the performance of your app. And the interpolation itself of the animations, I would say it's like free, you know.
Thank you. Comparing to Lottie approach, how lightweight, effective, complex SwiftUI animations are?
Well, I would say that especially if the Lottie approach, designer gives you what he wants to have, and you just put it in your app, and it's like he's requesting, you know. If you are doing these animations by yourself, you have more power and more control over it, but of course you might get into the situation that it will be not what your designer wants from you. But it's much easier to create these, I would say, interactive animations. So as we see, for example, this gummy slider, it's much better that you can control the behavior of such components, what animations, and really the tiny things, you know, what happens if user is sliding and then takes the finger away, how it should move back to the state or some state. So you have really much better power on these animations. But in terms of, for example, loading animations, it's completely fine if you get it as a black box or purely defined by your designer and then use it.
Thank you. And last question here. Do you know what bleeding function is used for the interactable animations?
Honestly, I don't know, but I think it's just like cross blend function. So I don't think it's being weighted in some more sophisticated way.
Thank you. Unfortunately, we don't have time for more questions, but the speaker will be at the speaker's corner. It's in front of this room. There, it's like a red stall where you can continue asking questions to the speaker. So thanks, Pavel, a lot. Now you can, in Slido, you can rate the talk and the speaker for our future mDevCamps. And there is a lunch prepared for you in the main foyer. So please enjoy lunch, and talks will continue here at 12:10. The next talk after lunch will be Igor Rosocha. He will be talking about e-doklady. Thank you.